In this lecture, I want to discuss bivariate normal random variables again. And I want to start with a different approach and get to what we were doing before. I know if you recall from the previous weeks, we had defined a bivariate normal random variable with these parameters as a pair random variables given by this joint density function. And I just pulled the density function out of the blue and I just said, this is the answer, just take it. And I said that we would give meaning to 0, mu1, mu2, sigma 1 squared, sigma 2 squared later on. So today I will start that process now of getting towards the meaning of this these terms. These terms mu1, mu2, rho, sigma 1 squared, sigma 2 squared, and why the joint density looks like this. So for this, I will need to just go back a little bit and just start with something we just did the previous lecture about moment generating functions, and then come back to this this concept in a second. So what we'll first do is we will define a moment generating function for a pair of random variables. So let me just call it joint moment generating function. So here what I'll do is the following. I'll say suppose, so we write it in black as usual, suppose x and y are two random variables. Then M from R cross R to the real line given by M of S comma T is expected value of e to the Sx plus T times y. This is called the joint moment generating function. For x and y. So just remember, it's just a little different from the other one. Let me just make some space so you all see it clearly. So make some space, sorry. So the idea is that this is a function of two variables. So of S and T. Before, the moment generating function was only one variable, but now two variables. So this is so sometimes people write it as M sub x of S comma T. That's the same as this guy. So M sub x of x comma y of S comma T. Just to sort of make sure that you understand what two I'm talking about. Again, this moment will exist or not exist depends on what the expectation revolves around. Sometimes this moment may be infinite or finite, but whenever it's finite, we'll take the function as well defined. So this may not be a well defined function for everybody in S and T. So whenever it exists, so just make a note: the expectation may or may not exist, and the definition is valid when the expectation exists. Very nice. So now the main punchline of this whole theory of this joint one is the following. That let's write some facts down. So these facts I will not prove. Again, this is available in my book in Theorem 6.3.9. This is what I was alluding to in the previous lecture as well. That the moment generating function kind of determines the distribution. So first let's go back to the one variable one. Suppose you had suppose we had random variable, let's say u and w. V and w are random variables with moment generating function function, let's say m sub v of t and m sub w of t for t in R. And again, I write t in R, but I think of it as only when the things are defined, we call it m sub w of t, m sub v of t, otherwise you just don't bother about, you say it doesn't exist. So we have two things. What's cool is the following. If m sub v of t is the same as m sub w of t, right, then in t in I, where I is any open interval, so you have the two moment generating functions agree in some open interval, then this is enough to conclude that the two are the same distribution. Then x and y, sorry, u and v and w have the same distribution. V and w have the same distribution. That's the one variable case. Now let's do the two variable case. The same thing applies. So suppose you have a pair, let's say xy and zw, let's say, so or zt, let's say. So let's say suppose we had two random variables pairs, let's say xy, and let's say let me write y properly, capital Y, and let's say zt as two pairs of variables, are pairs of random variables. And again the same thing. So suppose you have the joint ones, m sub xy at the point t is equal to m sub z comma t at the point, let's say s comma t should be there, sorry, so two variables, so s comma t in some rectangle, for some s comma t in some rectangle. So here we just call it open rectangle in R2. Then again the same thing happens. Then the joint distribution of x and y is same as joint distribution. Then that's if and only if the joint distribution of x and y has the same distribution as z and t. Very nice. So that means this fact tells you that the moment generating functions determine the distribution. So this is called the uniqueness theorem. It's a very important fact one can use. So if you want to show two things have the same distribution, all you do is compute the moment generating functions and they match up, you're on your way. And similarly, if you have two random variables and you want to understand if they have the same joint distribution, you go and find out their moment generating functions in an open rectangle, and if they agree, then you conclude the two things are the same. It's quite a powerful theorem. This is very nice to keep in mind. I like it a lot. Okay. Now let's try and use this idea a little bit further. Let's go back to our normal example again. So let's say I take an example. Let's say an example again. Let me go example. Sorry, example. Suppose I did not know this fact. Let's say so. Let's say x was normal with parameter mu and variance sigma squared. Before let's say I know this. Then a long time back I had shown you that y equal to x minus mu by sigma was normal 0, 1. We did this by brute force calculation in the previous course. Now let's try and show by this moment generating function method that these two are the same. So what I'll do is I'll just look at m sub y of t. So what's m sub y of t? It is expected value of e to the ty, right? And what's that going to be equal to? That's going to be equal to e to the t by sigma times x minus t mu by sigma. That's just the definition of the thing. Right? Now this is just going to be equal to e to the minus t mu by sigma. That will come out, right? They'll come out, and inside what I'm going to have, I'm going to have expected value of e to the t over sigma times x. Right? But this is what now, this is just same as e to the minus t mu by sigma, and this is just mx at the point t by sigma. That's exactly what I'm doing. This is the more generating function evaluated at this new point t by sigma. But this we know from before, from the previous calculations, is like e to the minus t mu by sigma, and inside what I'm going to have, e to the mu times at t, I'll have t by sigma, then I'll have plus 1/2 sigma squared, right? Sigma squared into t by sigma, the whole square. This is what I'll get. And this, if I do the algebra, I'll just get equal to e to the t squared by 2. Everything else cancels off. And but this is the same, but alas, this is the moment generating function of normal 0, 1. Moment generating function of normal 0, 1. Random variable. So this implies that y is normal 0, 1. So now it's another proof of showing that if x is normal mu sigma squared, y is x minus mu by sigma, then y is normal 0, 1. Just compute the moment generating function and show it's the same as normal 0, 1, and then use the theorem to show that this is by this fact, right? It's by fact. Just call it by facts. Very nice. It's another interesting thing about normal random variables, and but I will need something about moment generating functions, which I'll use to show this this kind of interesting fact. Let's try and do that in a second. So now, I'll call this another example. So I'll use another fact about normal and moment generating functions that go along the way, but let me just do it as part of the example itself. So let's say, suppose x is normal with parameter, let's say mu1 and sigma 1 squared. Okay, I'm trying to get towards bivariate normal, so that's why I'm using all these terms again. And y is normal with mu2 and variance sigma 2 squared. I take this one. So and let's say x and y are independent. Once you have this, then the first thing you observe is that m, let's look at the random variable z. Let z be equal to ax plus by for some a and b in R. Okay, so I'm just going to take a linear combination of the two normal random variables. Okay. Now, if I take m sub z of t, right, that's going to be equal to what now? Actual value of e to the a times tx. Sorry, let me write this properly. E to the tz, and that's just expected value of e to the a times t of ax plus by. Okay. And that's going to be equal to what now? That's going to be expected value of e to the t times ax times e to the t times by. Now here's the crucial fact about MGF that I'll use. That is, this person is independent of this person because x and y are independent. So as x and y are independent, this implies that e to the tax implies e to the tax and e to the tby are also independent. So once you have this, the top guy is going to become expected value of e to the tax into xy value of e to the t by, because the independence will just split the two things into two parts. But what is this now? This is going to be equal to now, this is going to be equal to just this is just going to be equal to mx of at at the point at into my at the point bt. That's one thing we observe, right? This is what we observe. It is any linear combination will give you this mx of at is my of bt. Now this is one fact that I have derived. That is, if you have z equal to ax plus by, then mz of t is going to be given by m sub x at times m sub y bt. Right? But we know this. So what is m sub x at? X is normal with parameter mu1 squared, mu1 sigma 1 squared. Y is normal parameter mu2 sigma 2 squared. So this means this is going to be equal to, so let's write this down. So the first term is going to be equal to what now? We move across this way. First term is going to be equal to what now? Exponent of the first one is a at a mu1 t, right? That's the first one, plus 1/2 sigma squared, and then you have a squared t squared, right? That's what the first one is. And the second one is e to the a mu2 t, right? And it's going to be 1/2 sigma squared b squared t squared. That's what, so b times this is what it's going to be like. So if I combine everything together, what do I get? I get e to the a mu1 plus b mu2 of t, right? And then here I'll have 1/2, right? So 1/2, let me write properly, 1/2. And what do I have inside? I have sigma squared a squared from the first guy, sigma squared b squared second guy, right? So I'll have this. So there'll be a squared sigma 1 squared plus b squared sigma 2 squared times t squared. That's what I have. So what did I start off with? I start off with, let me go back slowly. I start off with m sub z of t, right, on this side. That I wrote down as first as this. Then I wrote down that as this a of this. Then I looked at the algebra. It just came out to be a function of e to the aty and e to the atx and e to the bty. But they're also both independent, so I could do this calculation. I could split them up as two different things, and that's the same as the homogeneous function of x at at and any function of y at bt. But both x and y, the distribution we know is normal mu1 sigma 1 squared, and y is normal mu2 sigma 2 squared. So once you do that, you can replace mx at as this expression right here, my bt as this expression right here, and you combine the whole thing out. Right? Now let's stare at it a little bit. So it means what have I shown? I've shown you z is equal to ax plus by, then mz at the point t looks like something like e to this at t times e to this at t squared. So now again, by the moment generating function fact, something you can check. So now by uniqueness theorem again, so uniqueness theorem again, that is, two moment generating functions have the same distribution, same moment generating function has the same distribution, but this we know is the moment generating function of a normal random variable, this mean and this variance. That's exactly what it is. So that means this implies that, and the fact and the fact about normals, fact about normal random variables imply that z is distributed as normal with this mean, this parameter, right? This parameter a mu1 plus b mu2, with mean a mu1 plus b mu2, and the variance is exactly this parameter right here. So a squared sigma 1 squared plus b squared sigma 2 squared. Quite cool. So that means if z is equal to ax plus by, like we did here, then z is distributed as normal with parameter a mu1 plus b mu2 and variance a squared sigma 1 squared plus, let me make it clean, so a squared sigma 1 squared plus b squared sigma 2 squared. Very nice. Right. So now I'm going to close this session by giving you a different definition of a bivariate normal random variable. Okay. So this is definition 2. It's the same as definition before, but I want to just close with this for today. We'll come back and then work on this as we go along. So definition 2. So we'll say a pair of random variables x and y. A pair of random variables x and y is called bivariate normal. So here I don't specify any parameters. Okay? I'll say bivariate normal. And it's motivated from the above example. It's called bivariate normal if so a pair, let me call it xy, x comma y. If the following happens, if ax plus by is normal distributed, okay, is normal distributed for all a and b, for all real numbers a and b. Okay, just notice that I'm not assuming anything about xy. All I've said is xy has this property that if you take a linear combination of them, then they are also normal. Okay, this is one thing that I want to keep in mind. We know one thing. If x and y are a pair of independent normals, the previous example showed the linear combination also is normal. Okay, but this definition says I take any pair, I call it bivariate normal. If for any linear combination of x and y, ax plus by is normal distributed. Okay, so one thing is let's say some consequences. Let's close with that for today. Close with that today. So like I said in the example, from the previous example, right? So from the previous example, let's say from previous example, if x and y are independent and normal, then they are bivariate normal. Right? So x and y are independent and normal distributed, then this implies that xy is bivariate normal. That's one factor you need to get right from the previous example, from the previous calculation. Because the previous calculation showed that x and y are independent normals, then the linear combination was always bivariate, or not always normal. That's the definition of bivariate normal. That's one thing, right? So next thing we can also say is that, let's say x and y are bivariate normal. That means they have some joint density. But all we know is that the linear combination is normal. That's one definition. But let me do a simple linear combination. Let me take a equal to 0, b equal to 1, and a equal to 1 and b equal to 0. Right? So if I take these two combinations, if you just stare a little bit, then what will happen? If I take a equal to 0 and b equal to 1, then this implies that ax plus by is equal to y. And this implies that ax plus by is equal to x. And from definition, this implies that x and y are x is normal distributed and y normal distributed. X is normal distributed and y is normal distributed. What am I writing so bad? Right properly. X is normally distributed and y also is normally distributed. Very good. So it means bivariate normals have marginal density normal. And this is a new definition. I will come back and get back to you later on. The converse will not be true. Huh? That's one thing to keep in mind. If you have x and y are individually normal, then you may not have bivariate normal. That we'll come back and check later on. But if they're independent, then it's normal. Bivariate normal. It's no problem. Very nice. So I will come back to this whole bivariate normal again by various definitions, and in the end I'll show everybody is the same. Thank you.